Yes, as John says, my name is Matt Raitt. I'm actually a mechanical engineer by trade, and we were the Passive House consultants on the project, working with the architect CPMG, with Richard, who's actually in the room, and the builder Interserve, who are actually the occupier of the building, who are also in the room. We work with structural engineers, BWB, so it's a design team that we're all very familiar with as parties, the architects, the engineers and the structural engineers. And we worked for the developer Rangeway, who I'm going to talk about as we go through. So this is the building. As you can see, I'll be referencing this throughout. This is the south facade with the increased glazing proportion. Okay, so just running through the contents, just going to speak about why we went for Passive House, certainly from the developer's side, why they wanted to go for it. A brief overview, as I'm sure you've all heard many times today, of the Passive House principles. How that was then implemented on this particular building, and some of the key lessons that we've learned from that process, and really the lessons that you learn in taking the residential principles of Passive House and applying them into a non-domestic place. Okay, so first of all, why did we go for it? Rangeway are a developer with many existing buildings, and obviously increasing energy costs in those existing buildings, inefficient standards. So they were keen to look to a new energy efficient office. As John mentioned, the Passive House principles was sold to Interserve, and they were very keen therefore to then, sorry, I'm away from the microwave, to implement that. So they actually then approached Rangeway, the developer, and got them on board. So from the very start of the project, we had the developer, the builder, and of course ourselves, all promoting the Passive House principles. As you can see, we did a quick exercise early doors to try and compare the energy savings that we were hoping to achieve versus other typical practice standards. So these figures are actually taken from Econ 19. As you can see, the main sort of savings are in the space heating demand, which is the green bar that you can see up there. But roughly speaking, we're using about 45 kilowatt hours per metre squared as opposed to the traditional 220. That's measured in real energy rather than the primary energy, which we'll speak about in a moment. Okay, so quickly covering the principles of the Passive House design, keeping the space heating demand below 15 kilowatt hours. As you can see there, we put up typical as a reference point versus the Econ 19 references. So we're at about 20%, something like that, of a typical practice, with the south-facing glazing and very efficient fabric. The second criteria is to limit the cooling demand on the building. So we'll come back to that in a moment, because a very important principle is getting that the conflict between having lots of south-facing glazing for beneficial solar gain versus the overheating, which as engineers is our usual concern and headache with office buildings and most non-domestic buildings, schools, albeit. The third criteria is the primary energy demand. So it's very much a case of working with Interserve about their IT strategy for the building. And we spent a long time going through all their various aspects of their primary energy demand, which we'll come on to. And fourth, of course, airtightness, and working with the builder and with the architects to try and improve that airtightness for the building, which is critical. So they're the four criteria that we're going to hit. I'm just going to skim through how we implemented them. Okay, so space heating demand. This is actually a block that the building was built out of. It's a Duracell block, it's called. It's a wood chip, or reconstituted wood, in a cement-based resin, which forms a block, which is effectively your formwork. One half of the block has insulation within it. The other half of the block is open then, in which concrete is poured to form the structural stability of the building. So therefore we've got the thermal mass half of the block on the inside of the building, which we look to use in our passive cooling strategy, which we'll come on to. So basically that's the fundamental of the building. So how do we get the space heating demand down? First of all, we looked at the orientation. We worked closely with the architects in the first place to ensure that we got plenty of south-facing facade. We introduced the glazing on that side, as we spoke about earlier, and we saw the first picture. I'll come back to the implication of that on the passive cooling side. So we're able to orientate the building very well. We've got super insulation. I mean, the window U value varies depending on which window you're looking at, but it's typically around 0.7. I think the mid-pane U value for the glass is about 0.5. The walls are 0.12, and that's with extra insulation on the outside of the Duracell block. So we have the Duracell block, and then we have an extra outer skin of insulation before the timber cladding is put onto that. And we have our heat recovery on the ventilation, which obviously is fundamental to what we're doing. We've actually used a Pitchler unit. It's an air handling unit, it's Passive House certified, it's from Austria, and the heat exchanger recovery rate on it is around 83%. So therefore, with all these three aspects, we're able to minimise the space heating demand down, and the space heating demand as determined for by the PHPP for the building is between 11 to 12. Depending on whether you believe ours or the Institute's version of the spreadsheet. Okay, so the flip side to the space heating with the south facing is the passive cooling, which becomes a fundamental aspect of it. This is actually a picture of the earth tube, similar to Sabrina's building earlier. We've actually used a grid formation, so rather than running around the building, we have two large header pipes and a series of smaller pipes to increase the surface area that's then exchanging with the ground from the tube. So as you can see there, it's, I think it's 30 metres long by 12 metres wide, so there's a grid of 12 smaller pipes across the two header pipes. So the three main aspects of achieving the passive cooling. The first one's thermal mass. We were able to integrate thermal mass. This is in terms of adopting it as a night purge strategy. So hopefully you're familiar with that in terms of filling the building with cold air at night. That gets absorbed into the fabric, which then helps to keep the building cool the following day. So in order to absorb that cool energy into the fabric, we need heavyweight materials, which is where the thermal mass comes in. So at ground floor height, we're able to use the underside of the soffit, the first floor planks, as our source of thermal mass. But up on the first floor, we've got an open ceiling, which we'll see a picture of later on, but a lack of thermal mass. So we've got some thermal mass in the walls, but we look to introduce a earth tube system. It's a proprietary product by Rehau, which not only helps in terms of space heating demand because the incoming supply air is preheated, it's tempered, but it adds a massive benefit in terms of limiting the number of hours of overheating in the summer, and we certainly wouldn't have met the recommended guidance in terms of overheating without that earth tube strategy. The second fundamental part to the passive cooling is the facade. So we've got a combination of solar glass, but more importantly, we've got an external blind system, a Levelux system, which is fantastic as an engineer because you are able to capture the solar gains when you want them during the winter or, say, for example, at weekends. But as soon as we don't want them anymore, we've got a means to turn them off, which as an engineer is a really fantastic design solution. And especially in this context, because an office building, whether it's built to passive house or otherwise, the majority of new office buildings, as soon as they're occupied from 9 o'clock, they no longer require any heating anyway. So it's all about the passive cooling approach. So the blinds are fantastic from that point of view. In addition, then we've got mixed mode ventilation. So as James finds, it's a good final backup option if everything else is getting too hot, if there's an over occupancy. Similarly, there's times of the year where the most efficient approach is to open the windows. For example, if the outside air temperature is around sort of 15 degrees, there's no point in running the earth tube system, the fan power that's used there. It's much easier to switch the ventilation off and just rely on the opening windows. So we've got a form in the building that allows us to do so. We've got a 15-metre footprint with windows on either side to create that cross-ventilation strategy. So it's really a fundamental part of it is that passive cooling approach, much more so than the passive heating approach, which is one of the main lessons learned, really. So this is the first floor, as I spoke about before. So it's an open ceiling above the steelwork. We've got exposed services. So our ductwork runs down the centre of the building. As you can see there, it's a supply duct that's running down, feeding off to various grills. We actually extract back at one end of the building. We're quite fortunate in this scenario because we were able to play with the architecture and we orientated it such that the extract was located behind the server room. So that, one, we didn't need any air conditioning for the server room, and secondly, we were able to benefit from the heat output of the server room that normally you're trying to get rid of. In the winter, we can then absorb that into the heat exchanger and therefore further reduce the amount of space heating demand. The PHPP isn't capable of taking that into account, but we're hoping to realise some extra savings in the actual consumption. So again, yeah, that was quite a useful lesson, and because we were able to dictate where things were, it worked really well from that point of view. So reducing the primary energy demand, we sat down with Interserve and went through a list of all the information, all the equipment that they were hoping to introduce into the building. There were various jokes made about typewriter departments or working at home or only working on iPhones and all the rest of it. But we got there in the end. There was various toing and froing that needed to be done in terms of their list of equipment. Fridges was one of them. A new server system for Interserve was another length that we had to go to in the end. But again, we were able to work with them and work within the constraints and just try and realise where we could implement new technologies such as the server, but at the same time where we had to take forward some of their existing equipment. I think one of the main lessons main headlines that came out of it was that we convinced Interserve to go away from their traditional one printer per person on each desk and swap that into a centralised printing system. So they had, I think, 2 printers in the end and a plotter, again, which we were able to locate back into the room with the server room so that the beneficial heat gains were taken into the extract ventilation stream without it going into the main office. So again, simple placement of rooms was able to make that a benefit rather than a problem in terms of heat gain.
5 minutes?
Okay. I'll skip on. This is Ian, the site manager, who deserves great respect. He gave blood, sweat and tears to this project. This was on the morning of the air tightness, where we'd calculated the 0.6 requirement as passive house. That translated on this building into Part L terms as a air tightness rate of 1.19 metres cubed per metre squared per hour at 50 pascals, which is the units we're all a bit more familiar with. So that was their limit, 1.19. And they actually went on to achieve 0.885, which was a great both relief and celebration all at the same time. It's a great testament to the build quality and the lengths that Interserve went to. Some of the key aspects in achieving that air tightness level, they appointed HRS as an air tightness consultant very early on in the project. And they came in, and what I think one of the main rules that they left with us was that every drawing was to have the air tightness line marked on it, which is sort of common sense when you think about it, but it made a big difference putting a big red line through all the architect's drawings that then could be then put onto the services drawings. And then you got this, the services contractors suddenly asking what this is, and everyone's a lot more aware of it. The guys on site are a lot more aware of it, and for no cost whatsoever, putting the air tightness line on the drawings was a really good, strong lesson learned. Achieving the air tightness in terms of penetrations was another one. So looking at service penetrations and using proprietary products. I mean, there's various different ways of achieving it. But certainly spreading service penetrations was one lesson that we learned. So in terms of cable penetration, for example, you can't bunch the cable penetration because you'll never seal around a bunch of cables. We found that you had to space them at 40 millimetres so that you've got individual penetrations, which does create quite a large area, but as you can see, the proof's in the pudding, so they've got the air tightness level down there. Other air tightness lessons that were learnt was a 10mm beading around all of the details, so everything's got a 10mm mastic shadow around it. And I think just some of the architectural details was the other one. HRS were able to come in and say, if you did it this way, if you did it that way. And like I say, the proof's in the pudding. So some of the lessons learned. Like I say, solar gain is the key lesson learned, really. And the fact that we've, if anything, I mean, I'll try not to say it within serving the room, but we've got too much glazing, if anything. So in future, we'd look to reduce that, which in turn would also reduce the cost. Sorry, guys. The next one would be guttering. We had a lot of trouble in terms of achieving the thermal bridge-free design. And the inboard gutter, for anyone that was in those long and arduous meetings, was a real sticking point. And I think the main lesson to learn from that was that when you jump into the supply chain, if you're suddenly trying to challenge the norm of how they construct things, you'll hit a lot of resistance. And we said, no, come on, we can do this. And they kept on wrapping metal around their entire element, which of course created thermal bridges. And it took a long time to get them on board with what we were trying to do, whilst also maintaining their warranties and everything else. And that's quite a key lesson to learn. And if anything, I think a couple of extra weeks at that tender period to develop that would really have helped. Passive cooling, which links to the solar gains we spoke about before, and ICT, again, I think is one of the main lessons learned. We've also got a lot of energy monitoring going on the building. It's only opened in August, so we're hoping to have some figures soon to be able to validate the design stage figures. So fingers crossed on that one, we might have an update for you next year. So it's just really a summary. I should have pressed the button a little bit earlier. Just quickly looking, if I can, just at the cost of the building. Interserve's existing stock, so really these are the numbers that drove the project. They were spending just over £23,000 a year on energy. We did some figures early doors, the graphs that I showed you, which showed that it'd be around the £3,000 per annum mark. The developer's taken this literally and put a massive sign on the site saying £2,830 per annum, which sort of drive past looking ominously at, but says Matt right. Yeah, with my photos, didn't it? So they're looking at saving approximately £20,000 per annum. This shows that over a 10% annual fuel increase rate, the accumulated saving is around 320,000. So therefore, there's an extra over cost of 180,000. The payback was around 7 years. And there we go. A brief summary. So obvious cost savings in terms of running the building. The actual quality of the product is very, very high. The initial feedback from Interserve is fantastic. The occupants love it. There was a very hot week about 3 or 4 weeks ago. And John gave us some data when it was, I think, 28 outside, and was it 22 inside, John? Which is great, which shows that the rehouse system's working. And again, from our point of view as engineers, we were always most nervous about it overheating rather than underheating. So the fact that we've had that week with a low sun angle as well, we're hoping is the worst case scenario, and we're over that now. Obviously, there's low maintenance. The systems are very simple systems. It's not overly complex, therefore the maintenance is relatively small. And obviously, it's very attractive in terms of attracting tenants and future potential tenants for Rainsway as a developer, which they're now looking to implement across a couple of their sites, actually. Okay, thank you very much for listening, and any questions?